Good evening. My name is Palak Jain. Today I'll be presenting joint work with Ron Canetti, Marika Swanberg, and Mayank Varya at Boston University on universally composable analysis of secure messaging protocols. Every day, billions of people use instant messaging apps to communicate over the internet, a large fraction of whom use apps like Signal, Telegram, and WhatsApp to protect their communications. Our work focuses on the Signal protocol. Secure messaging applications like these propose their own set of complex problems that don't exist for the frameworks considered in the past. Consider, for example, a client-server setting like the one for TLS. In this setting, the session duration is limited and both parties are online and able to talk back and forth for the entire length of the session. For an application like this, it's standard to perform some sort of initial key agreement followed by a secure communication, since there's no expectation for sessions to recover from break-ins. In contrast, instant messaging applications have unbounded session duration. A conversation between the parties could last even for multiple years. And the parties may be asynchronous, which means that they don't ever need to be online at the same time. For example, maybe Alice was on a flight at some point while Bob was messaging her, or maybe Bob was asleep when Alice was messaging him, and so on. Since this setting is long-lived, parties need to be able to recover from past corruptions. This requires continuous renewal of security via some sort of continuous key exchange mechanism. The Signal protocol that our paper focuses on really spurred the conversation about secure messaging, and many works since have tried to untangle the security requirements of the setting from the protocol itself. I'll very briefly overview related work before getting into the rest of this presentation. So there's a long line of research into the design and analysis of the Signal architecture and its subcomponents, as well as variants of the Signal architecture. And I will briefly discuss some of this work right now, but I'm going to apologize in advance because I'm really not going to be able to do justice to this part of the discussion. However, I will point you to our paper for a more detailed discussion of related work that is not subject to time constraints. So back before the pandemic, at the start of my PhD, we set out to do an analysis of the Signal protocol and its subcomponents in UC. And then very recently, while wrapping up our project for submission, we noticed this other work by Beanstalk et al. That we're soft merged with at this conference that also analyzes the Signal architecture in UC. So I'll begin this discussion by mentioning a few ways in which our works differ. So their modeling, unlike ours, does not account for the session initiation process, the private key infrastructure, or the parties' long-term modules that are an integral part of the secure messaging application. Their secure messaging functionality includes the network delivery of packets, which weakens their modularity and inhibits the use of Signal as a subroutine within larger functionalities. And while their modeling of Signal protocol follows the traditional partitioning into modules, it does not formalize this partitioning within the UC framework. So by contrast, we modularly pull apart the different components of the protocol. And in particular, we pull apart this key exchange component that's responsible for the renewal of security, despite the circularity in the architecture. Additionally, the concurrent work models all key derivation functions as random oracles, while we show a plain model instantiation of this primitive. On the other hand, though, there's a gray period during recovery from compromise where partial security has been restored, and their work actually models a partial guarantees provided during this time, while ours does not. Their work also accounts for adversarial choice of randomness, which our model does not account for. I'll just say one more thing about this gray period during recovery from compromise. Our work actually kind of considers this still as part of the compromise. So the parties are still fully compromised during this time in our functionality. So the other composable model for message transmission and ratcheted key exchange was provided in the work by Jost et al. In the constructive crypto framework. And finally, I'd like to mention that while this work is inspired by the clear game-based modeling and analysis of Signal in works like the one by Alwyn et al., our model differs in a number of significant ways. For one, our analysis provides a composable guarantee, and secondly, we directly model security against a fully adaptive adversary that decides when and whether to corrupt a party based on everything it's seen so far. And this is different than the notion of adaptivity that's used in prior work, where the adversary has to decide its set of party corruptions ahead of time. So what do we do in our work? In our work, we provide a model for secure messaging in the UC framework, and we analyze the Signal secure messaging protocol with respect to this model. Concurrent work by Beanstalk et al. Provides a slightly different UC model for secure messaging and analyzes the Signal architecture with respect to that. The next three contributions, however, are unique to our work. The first one is that our analysis of the Signal architecture is done in a modular fashion, which means that in addition to the model for secure messaging, we actually model each component of the architecture separately in UC, and we consciously keep each of these component functionalities as general as possible in an attempt to enable future work to apply them directly. This modularity forces us to get around an inherent circularity in Signal's architecture, which we will discuss more in detail shortly. Secondly, as mentioned before, our adversarial model is completely adaptive, which means that the adversary can decide when and whether to corrupt a party in the moment and does not have to provide this beforehand. This is also done by the concurrent work by Beanstalk et al. The difference between our works is that we make very limited use of the random oracle model. So in particular, we provide a plain model instantiation of the key derivation function that they model as a random oracle. Finally, we define a new primitive, and our primitive models the adaptively secure key derivation functions that we just mentioned a second ago. And this key derivation function is essential for the Signal architecture. And specifically, our model will make explicit the need to simulate the internal state of the parties in the face of adaptive corruptions. Our plain model instantiation of this primitive is actually what allows us to provide an implementation of Signal that achieves adaptive security with minimal use of the random oracle abstraction. I'll also say that I'll talk later about, when I talk later about the cascaded PRF-PRG construction in our work, I'll also mention its comparison to the PRF-PRG by Alvin et al. Now I'll mention our adversarial model. So the adversary has two types of powers. The first is full control of network delivery, which means that the adversary can delay, spoof, and drop any packets of its choosing. And the second adversarial power is instantaneous corruption of parties, which means that the adversary can corrupt a party at any moment and be given the entire state of the party at that time. So we are ready to jump into a description of Signal, starting with a description of some of the guarantees that it provides. Imagine that an adversary corrupts Bob at some point in the conversation. Then the first property is that all messages received before the point of corruption are still protected. And the second property is that the parties are able to eventually recover full security under certain conditions. To provide these two guarantees, which are forward secrecy and post-compromise security, parties perform continuous key agreements, which allows them to add randomness into the system. But despite this continuous addition of randomness, the protocol guarantees what it calls immediate decryption for messages that arrive out of order. It also guarantees that the parties can figure out the order in which the messages were sent once they decrypt them. So most of the heavy lifting in the protocol is actually done by a complex key sharing system within the architecture, and then the parties use the keys that are spit out by the system to encrypt each message. And they encrypt each message that they send to each other under a different key. So, I'll talk briefly about the actual protocol now. So when Alice wants to send a message, she uses the key exchange instructions to compute a new key. She uses this key to encrypt the message and then sends the encrypted message to Bob across the adversarially controlled network. When it's time for Alice to add new randomness into the system, she first chooses a new Diffie-Hellman key pair. She incorporates this fresh randomness into the computation of an encryption key that is used to then encrypt the message. And then it's sent across the network to Bob again. But now to be able to decrypt the message, Bob needs to compute the same key. But for this, he'll need to know the Diffie-Hellman public half, to be able to incorporate the same randomness that Alice used. So Alice will send this Diffie-Hellman public key to Bob as a header along with her encrypted message. But there's one more problem. The network is adversarially controlled, so this header could be tampered with. So she also puts this header inside the encryption as associated data, and so it gets authenticated by the encryption key. This brings us to a point where we're ready to talk about the functionality for secure messaging, which we intentionally keep as a very simple interface. So when Alice wants to send a message M, she'll ask the functionality to encapsulate this message for sending and directly forward the return ciphertext header pair to Bob across the network. The header here indicates where this message fits in the conversation, but instead of using sequential numbers to track the progress of the conversation, which would directly reveal some information about the length of the conversation, we actually allow the adversary to pick new identifiers all the time that represent the epoch of conversation that the parties are in. When Bob receives a ciphertext header pair from Alice through the network, he checks that the message decrypts and authenticates successfully. And he does this by asking the functionality for a decryption. And if this authenticated decryption succeeds, then Bob gets a message M. And if it fails, then he gets a failure notification. Now, in the full functionality, Alice and Bob can actually send as many messages one after the other as they want without waiting for anything. But and this is very important for the usability of a secure messaging system. But for the purposes of this talk, I'm going to abstract that part away and assume that the parties send one message at a time, and then they wait for a successfully decrypted message before they message again. This will actually allow us to abstract away one of the two key exchange modules from the signal architecture and really zoom in on the one that's responsible for renewal of security and therefore kind of zoom in on the circularity issue in the architecture. But the full version of the protocol is actually a simple extension using some of the modules that we define in our paper. And specifically, if you're looking at our paper for which modules kind of provide that extension, you want to look for the forward secure authenticated encryption and the message key exchange component. Next, I'll explain how despite the circularity in the signal architecture, we provide a separate functionality for the key exchange component that's responsible for renewal of security. And this will lead me to then be able to explain how we realize this functionality without needing a random oracle, which is thanks to our plain model instantiation of the primitive we define, which is called the cascaded PRF-PRG. Going back to the protocol, I'll put Alice's view on the right and fill in Bob's perspective. Once Bob receives the ciphertext header pair from Alice, he uses the Diffie-Hellman public key that's in this header to compute a decryption key K, and then uses this key to decrypt the message. If the header contains the correct Diffie-Hellman public key, then Bob will be able to compute the same key as Alice, that's K, and the ciphertext header pair should decrypt successfully. Otherwise, if the header has been tampered with or the ciphertext has been tampered with, then if the header has been tampered with, then the key computed will be different and decryption will not succeed. And if the ciphertext has been tampered with, then just decryption will not succeed. And essentially, while Alice knows that she's used her own Diffie-Hellman pair to compute the encryption key that she used for the message, Bob actually computes the decryption key using the header that he was sent or the header that he received and waits to find out if this is the correct one via successful or unsuccessful authentication under the key K. And so I'll just mention a small aside actually. Alice and Bob here are participating in Diffie-Hellman key exchange implicitly, which I'm kind of glossing over, but I'll explain that shortly when I explain the protocol more in detail. So the circularity issue that we need to address is that the key that authenticates the header is actually the key that we computed using the header. So instead of each party running the protocol separately, they interact with the same instance of the functionality, right? I should mention that I'm going to move on now to the functionality from this protocol. So let's do that. And the functionality itself works almost exactly like the protocol that we described, except for the fact that we don't restrict this randomness addition to the Diffie-Hellman key exchange. And so to model this, we don't have Alice make a choice of Diffie-Hellman pair, but instead we allow the adversary to choose the header that identifies the addition of randomness. This header is then sent to Alice along with the encryption key. And in the honest case, where the header is not tampered with during network delivery, the functionality will return the exact same key that it sent to Alice, to Bob. The main question is, what should the functionality do when the header has been tampered with during the network delivery, and how do we prevent the circularity, right? So in the case that the header is different, the functionality doesn't inform Bob of this error. It actually returns a new key that's chosen completely at random and leaves Bob to discover this mistake on his own. And so this requires that all incorrect headers produce unrelated random keys, and that will certainly get around the circularity in Signal's architecture. But the question is whether Signal's protocol is able to realize this functionality, and if so, how. Also notice that this kind of passive-aggressive thing where the functionality doesn't tell Bob whether the header provided was incorrect, but just provides a completely random key, means that the functionality can't directly know when Bob perceives a particular header to be the correct one. And so instead, Bob confirms the header through a confirmation interface. And if Bob confirms an incorrect header, then the functionality will enter a bad case, which we will model by allowing the adversary complete control over future key choices. So let's talk about whether Signal's protocol is able to realize this functionality. The key exchange module in Signal's architecture is the one that would have to realize this functionality. And it uses a key derivation function, whose properties I will discuss in just 1 minute. This function takes two values as input, a root key and a root input, and it produces two outputs, an updated root key and an encryption key. So Alice holds a message that she wants to send, but in addition to this, for this protocol, she holds a root key that she shares with Bob, Bob's Diffie-Hellman public key, and her new Diffie-Hellman pair that she just chose to kind of add some randomness into the system. So she uses the Diffie-Hellman values to compute a shared key, and then she uses that as input to the key derivation function. And then she uses the root key that was stored as the root key input to the key derivation function. And this gives her an updated shared root key, as well as the key with which to encrypt her message and authenticate her Diffie-Hellman public key. So, oh no, I just went back in the slide. I'll just go forward to where I was. Right. So this gives her the key with which to authenticate her Diffie-Hellman public key. So now Bob also holds their shared root key for this protocol, and he holds his Diffie-Hellman pair, for which the public half was with Alice. When Bob receives the network packet, he follows exactly the same steps to retrieve the key as Alice just did. So the key derivation function used by both Alice and Bob is the one that's going to have to provide the forward secrecy and post-compromise security guaranteed by Signal. And it also needs to satisfy the guarantee that we require in our functionality, which is that when you put in an incorrect header, then this will result in a pseudo-random key, which is what will kind of allow us to get around the circularity in the architecture. Lastly, Bob updates his stored key only if decryption succeeds under the decryption key that he receives or computes. If the header he received has been tampered with, then decryption will not succeed and he won't update his state. So he won't save a new root key or Diffie-Hellman public half. And this conditional update of Bob's state is what provides the conditional ratchet forward that's modeled by the confirmation interface in the functionality. So this brings us to the last contribution I'll talk about today, which is the new cascaded PRF-PRG primitive that we define. Our plain model instantiation of this primitive allows us to realize the key exchange protocol we just spoke about without a random oracle. And so let's talk about kind of the guarantees that we ask for. Prior works already observed that there's a few conditions under which the KDF must maintain security to provide the necessary functionality for the signal architecture. So if the root key is known due to recent compromise, but the parties' Diffie-Hellman and exponents are secret, then the KDF must maintain security. But also if the root key is secret, but the adversary tampers with network packets to insert Diffie-Hellman public keys whose exponents it knows, which means it knows the root inputs, even then the KDF must maintain security. So Alvin et al. Formalized this guarantee by way of constructing a new primitive, a PRF-PRG. And when both inputs to this primitive are unknown to the adversary, then it behaves like a PRF. And if only one of the inputs is known to the adversary and the other one is unknown, then it behaves like a PRG in the unknown, like a PRG in the other input. So what they did not consider is the need to provide a simulated state in the case of corruption, for the simulated state for the party that got corrupted. And so this can be a problem, right? So say Bob is holding some sort of root key and the adversary passes many incorrect root inputs to Bob to get, or not root inputs, but headers that he uses to compute root inputs to Bob to get many different outputs of message keys. And then none of these cause an update to Bob's state. So after that, the adversary can corrupt Bob to get the state that should kind of comply with all the outputs that it saw. And in this example, we actually run into the Nielsen bound because we have a constant kind of key, but we have many, many outputs produced from it. So we can't equivocate on those. And we formulate this new primitive that's called the cascaded PRF-PRG that extends this PRF-PRG concept that was introduced in the paper by Alvin et al. And what we do is we actually model the entire KDF chain directly in the presence of adaptive state exposures. Our primitive directly addresses the equivocation that's needed to handle adaptive state exposures and discusses two instantiations of the CPRFG, which is the abbreviation that we use for it. So the first instantiation that we discuss of the CPRFG in our paper is an immediate one that uses the KDF from the current implementation of Signal, but this is in the random oracle model. But the second is a new plain model protocol that we provide that's based on punctured PRFs. So since the adversary interacting with our key exchange module can obtain unboundedly many alternative keys for a given epoch, the Nielsen bound tells us that in the plain model, all the keys can't be generated using the same bounded size secret state. So we instead provide an instantiation using standard primitives, which is pseudorandom generators and puncturable pseudorandom functions, where the local state grows linearly with the number of keys requested from the key exchange functionality. And this is only true till the conversation advances. Once the conversation advances, the state shrinks back to its original size. To wrap up, our work provides a composable and modular analysis of the signal architecture in the presence of completely adaptive corruptions. We define a new primitive that models the security guarantee of a crucial component of the signal architecture in the presence of fully adaptive corruptions, and provide a plain model instantiation of this primitive from standard primitives. Future work could use the functionalities presented in this work to analyze variants of the signal architecture and its components. And please email me at palakj@bu.edu with any questions you have on the work in our paper, and see our full version on ePrint at the link on the slide. Thank you very much.